Okay, hello and welcome. My name is Craig Duffy and this is the first web seminar for the mobile and embedded devices. And we're going to be starting off looking at the Olimex boards that we'll be programming and the Linux operating system that we'll be using to do that programming. So first we need to take a look at the boards. Okay, so the boards we're going to be using are these Olimex boards, which have an ARM processor, which we'll be looking quite a lot of detail at. And in order to program them, because they don't really have any resources, we will need a jtag connector to connect them to our computer and a USB A-B connector. And the jtag connector is connected to the board, it's keyed so you can't really do it incorrectly, and you then connect your USB connector to the back of the machine. I'm using a virtual machine, so that's why it's asking that question. And you should see the power light come on, and you may also get some activity depending on what was less lying on the board from the last person who used it. So it might flash or do all sorts of things, but don't worry about that. Okay, so you'll have to have the board connected to a Linux machine, and really use the ones that are in the lab, because I can't guarantee the software in other places. So once you've connected the board, and if the power light comes on, if you're unsure about any of this, of course ask your lab tutor. And even though we're only using 5 volts, do be careful. If you're eating or drinking while doing this, then stop that, because you shouldn't be doing that in the labs. Okay, once the board is connected, if you type in ls USB, you should see in the output that the ARM USB tiny JTAG device is connected. So this means that the device has been recognized. And now we need to be able to connect into the machine, into the board, using some software, and the program we're going to be using is called OpenOCD, and it stands for Open Core Debugger, not Obsessive Compulsive Disorder, which you might imagine it could possibly mean. Now, in order to run it, we'll need a configuration file which will help some setup parameters, and the standard one that we've been using is called openocd.cfg, and this has got lots of interface details. Probably the things that worth noticing are those 2 values there, the port numbers that it is using for Telnet and GDB. So we'll call OpenOCD with -f for its command file and openocd.config there. And now we can see it started talking to the device, and you might even be able to see the light flashing on the device. Now, OpenOCD just sits there. It's a server program, basically, and it waits for other things to connect to them. So we now need to go to another window, and we need to talk to the OpenOCD program. And Telnet is normally used to talk to remote machines. In fact, it's not used so much now. SSH has taken over from it. But Telnet, it can be used to talk to remote machines. But we're talking to something locally, so we say localhost, and then the number 444, which, if you remember, was in the openocd.config file. And this now allows us to talk to OpenOCD, and you can see here that OpenOCD has noticed it's being talked to. So there's a number of commands that we can do here. I mean, obviously the simplest one is help, which will give help, and you'll notice the information comes on both screens. There's a command called reset halt, which stops the device from running. And this is very useful because if it is running, you can't type commands in, or if you wanted to run and find out what was on the device, then reset run, and maybe the device will do something, maybe it won't. Now, in order to start with this, because one of the things we want to be able to do is build some programs and download them onto the device. At the end of worksheet 1, you'll notice that there's some information on a test piece of binary which you can download. Okay, we're going to start by downloading some pre-built code, and I've created a small directory with first test.bin, which is the pre-built binary, and an openocd.config file so that we can run openocd. And if we look at first test.bin, ask Linux what it thinks it is, it just thinks it's data because it doesn't quite understand the binary. So with the board connected, we run openocd-f openocd.config and get openocd up and running, and then we telnet through. So we can run the series of commands, we can find out what the .cpu current state, and it tells us that the current state is halted. Actually, normally what you would do is you would just say reset halt because it can't really harm. So what we want to do now is we want to upload the first test bin and pop it into the memory on the board. Now, as we go on through the course, I'll explain a lot more about this. So some of this will perhaps seem a little magical at first, but just bear with it. So the first thing we need to check is that we've got some flash memory, and we can run the flash probe command and start at the bottom of memory, the 0 bank, and it's telling us that it's found some memory. It's even got a device ID, and we could look that up and find out who manufactured it and all sorts of information. It's 256k bytes, and it starts at this address. And this is standard for these ARM Cortex-M3 devices. Now, we can probe this, we can erase this device, because with flash memory, before you can write, you must erase. It's a very specific way of handling flash. So what we're going to have to do now is run the STM32F1X mass erase command and tell it that we're erasing bank 0, and it just comes back and says done that. Now, when you erase flash memory, you in fact write everything to ones, so that's how it erases, and when it writes it just simply goes around changing the ones into zeros where necessary. And we can see this by doing a memory dump and looking in the beginning of flash memory, so 8 and 6 zeros, and if we look at 100 bytes we'll see that they're all set to Fs. Now if I write in the new program, because it's been erased. Now on some systems you'll find, particularly like phones and commercial devices, that the memory will be locked and maybe password protected, and sometimes even hardware protected, so you might have to put some sort of physical device in a dongle or a key of some kind. But on these development boards obviously we could protect them, but they're completely unprotected. So we can flash and we can write a bank of memory starting at 0, and we tell it the name of the file, first test.bin, and any offset and 0. In fact, 0 isn't really necessary, it will do 0 by default, and it now says it's written that. So 636 bytes, 6,336 bytes at the location we asked. And if we now do the memory dump now, we'll see that this now has different data in it. And in fact, as we'll later find out, that is the vector table. So those addresses are quite significant, and we'll understand those later on. Now we can now execute the program, and it's terribly exciting. So if we do reset run, and then we should be able to see the program run. So here we can see the program running, and it just simply toggles between the yellow and green LEDs. Clearly not terribly exciting, but there you go. Toggling LEDs is something that you will end up doing quite a lot in your careers if you do embedded systems, and then reset halt stops it. Okay, we've now seen how to connect the boards, how to connect to them from Linux, how to upload some code onto the boards and execute the code. Obviously this code's been pre-built, so we can't really change it. So in the next few worksheets we'll be looking firstly at the tool chain that we need to use in order to develop the new programs, and then we'll start developing some code. So really it's a good idea for you to work through the worksheet yourselves, try downloading the programs, try playing around and seeing what happens, because you will need to have these skills in order to complete the later worksheets, and particularly the assignment.